So yesterday I gave you some of the main steps in the proof of Green's theorem, the version given by the improved version given by Helfgott and Andorotto. Now I stopped at some point. Probably I shall first review the structure of the argument because that's the main takeaway from the course, and try to verify the hypothesis that I put on the weight function V, and we will be able to verify most of the hypotheses except one perhaps, which is the bound coming from the restriction theorem. For that one would need a little more time to do, maybe another hour or so, which we don't have. But it easily follows, I mean, it's not a very difficult deduction from the large sieve inequality of the type that was covered by Shatadal in his course. There's actually a written up notes I have with me. I can circulate it to the participants to see the part of the restriction theorem. So apart from the restriction theorem, the rest we shall try to check here, and also the details of the argument to the extent we can within the time. So let me begin by writing down the statements slightly in brief. So what we want to show is that if A is, so this is the theorem, and that is if A is a subset of the primes between 1 and n, and the cardinality of A, the cardinality of A divided by the number of primes up to n is greater than some constant times triple log n by double log n to the power of 1/3, then T of A is not 0. So T of A was our notation for the number of non-trivial three-term APs inside A, namely the APs x, y, z with x, y, z distinct. Okay, so this is the version of, this is due to Helfgott and Andorotto. And to prove this, the strategy was to choose, so we set so okay, first of all we do not take n here, we prefer an x because we are going to change, n is going to be x divided by this w. Okay, so for the moment in the proof, in place of n, we'll consider the interval 1 to x. So we consider the interval 1 to x rather than 1 to n. So we write 1 to x rather than 1 to n, reserving n for x by w. Okay, so we just make this as some sort of parenthetical note. So now w itself is about 1/3 of log x. So you take, is the product of, so w is the product of all primes up to a z, and z is 1/3 of logarithm of x, taken as 1/3 of z. So all the way up to essentially constant times log x, whereas in green he had square root of log x, if I remember correctly. So it's a much longer product of primes that is taken in Helfgott and Rothon. Okay, then one argued that there is a B. So first for each B in 1 to W, we set A subscript B to be the set of n in Z such that Wn minus B is an element of A. Okay, Wn minus B is an element of A, and we also set Vn also Vbn is said to be equal to the weight contribution from the finite primes times log x if Wn minus B is a prime in 1 to x and equal to 0 otherwise. Then a simple averaging argument showed that there exists a B such that this sum 1 AB n VBN is greater than or equal to delta by 4 x by W plus 1, okay, n in Z. And then we also noted that VBN and ABN, both of these are, so VB is supported in 1 to x by W plus 1. And so also ABN and ABN is also contained. So given these facts, so this is the summary of the W trick which led us up to here, and on account of this we set n equal x by W plus 1, and we fix the B, fix B according to this. So according to this, let us say, according to this, and drop it from the notations. So we'll write only V, hence star is rewritten as one of this, no, one ABN is the indicator function of AB. Yeah. Yes. I mean, the fact that Wn minus B lies there. So star is rewritten as 1 to n 1A because your AB is now your A essentially, Vn is greater than delta by 4 times n. So this is your new situation. Okay, we just drop the b's, but you must remember, I mentioned it fleetingly yesterday, you must remember that your A and AB are related slightly different. You see, the condition for the definition of AB is that Wn minus B must be an element of A. Okay, so it's AB is those that the inverse image under this homothety, Wn minus B. Okay, it's not just a translate or something like this. There's a multiplication by W, and nevertheless, because it's a homothety, non-trivial one, it turns out that the number of the three-term APs in A and the three-term APs in AB are in one-to-one correspondence by this bijection. So you have, by this map. So therefore, counting AB itself is free from three-term APs. So here again, you have this set A, which is actually now AB, and it is free from the only three-term APs in it are the trivial ones. Okay, so you must just keep this small point in mind that there is the relation between AB and A is through this homothety Wn minus B. And then you have this weight function. By way of comparison with Roth's theorem, the situation was slightly different. So in Roth's theorem, the case was you had summation 1 to n, and you had just the characteristic function of A, and that is greater than delta times n. This was the situation in Roth's theorem. Whereas here, and then what did we do in Roth's theorem? We replaced A with a set B, which is more than a factor, 4/3 greater than the cardinality of A. Okay, and therefore had to have a large number of APs. It was much more dense, had to have a large number of APs. On the other hand, A and B were, in the Fourier sense, close enough that in fact the number of APs in B couldn't be much more different from that in A, and these two contradictory forces produced as the theorem. Okay, that was the situation of Roth's theorem. Here we don't exactly have a characteristic function. We have the characteristic function weighted by a natural weight for the primes. Okay, this is actually the natural weighting function for the primes if you forget the phi of W. So where was this thing? If you forget this is basically this is the 1 over log x, x over log x. So this log x comes from the density of the primes up to x, which is 1 over log x. So this is the natural weighting function. It's the reciprocal of the density. So if you multiply by that, you should in principle expect this to look like the characteristic function of a dense set in 1 to n, right? Whereas it's not, it's multiplied by log x. So what we are going to do is to devise a new function. So calling this f, so we'll call this f. We call this f, and then find a function g which is close to f in the Fourier sense, so that the number of three-term AP counts for g and f are not very different. On the other hand, we will see that g has some properties, namely that it's bounded in L2 in a reasonable way, which allows, in fact, us to say by Roth's theorem that the support of G is dense in 1 to n. And therefore, the support of G, first of all, by the properties of G, we will be able to say that the support of G is dense in 1 to n. Okay? So the support of G is close to A, G is close to A in the Fourier sense, and the support of G is dense in 1 to n. So this transfers the problem from A, which is a sparse subset of 1 to n, to the support of G, which is now a dense subset of 1 to n. And this allows you to apply Roth's theorem to G and then conclude the corresponding one for A. You see, you start with a sparse subset of the primes, you weight it by the density, reciprocal of the density of the primes, you produce a function which unfortunately is not the characteristic function of a set, but okay, it is like this. But the main problem is not a characteristic function of a set. So now you produce another function G which is close to f in the Fourier sense, and the support of that function is dense in 1 to x. So you have transferred the problem from the primes to the integers. Okay, this is the dense model sort of dense model lemma or whatever. Where this is called the transference principle. I mean, you transfer the problem from a sparse set to a dense set and then apply the theorems that you know for dense subsets of 1 to n, and then you are able to solve the original sparse problem. So in the K-term AP case, the longer AP's case that Gyan is dealing with, the problem in the natural numbers turns out to be much harder, Zemerides theorem, than the transference itself in a curious way. Now, I mean, after a decade of understanding this thing, it turns out that the transference is not as hard as proving the thing in the integers itself. Okay, so now let's get down to actually constructing this function G and seeing what properties of V give you such a G. So the properties of V that I listed yesterday the properties of V were so the properties of V so of course the first is that Vn is positive for all n and supported and 1 to n. So it's a positive finitely supported function, and secondly that the L1 norm of V, so L1 norm of V, which is same as this, is less than n. It's the second property. Third property was the L2 boundedness, perhaps E square n z less than or equal to some theta times n square for an appropriate theta which will be less than 1, and that's an important factor. It's using this theta that this theta is what controls the approximation. Then you have Vn plus m, n in z is less than n for all m not equal to 0 in z. So for the non-zero, the shifted convolution or the convolution, the shifted correlation products when m is not 0 is small. That's one thing. Finally, and rather important, is that the LP norm. So V LP is less than n to the 1 minus p. Okay, I should write it slightly differently. F LP less than 1 minus 1 by p for all p between say 2 and 3 here, and all f with 0 less than f less than v. What this means is that f of n is less than or equal to v of n for all n in Z, and f of n is positive. Okay, so this bound here, usually one would state it in terms of the L1 norm of V, but since the L1 norm of V anyway is bounded by n, this is the form that we'll finally need it in, and this is what is called the restriction bound, restriction estimate or restriction bound. So this comes from this is the restriction theorem for primes. You see, it's not immediately possible to appreciate the meaning of this name restriction theorem, because actually the restriction theorem, the name restriction theorem comes from the name of a theorem in Fourier analysis, where one asks if there is a meaningful restriction of the Fourier transform to the surface of a sphere or some submanifold which is of zero Lebesgue measure. So in principle they should, because Fourier transform of functions in LP or for a suitable P, the Fourier transforms are not defined everywhere. So, and if you have something that's of measure 0, it doesn't seem to make sense to talk of restrictions. Nevertheless, for certain values of P you can, and it's by means of certain inequalities that you prove that you are able to define continuous operators and extend them from Schwarz class functions to the appropriate LP spaces and so on. So that whole topic, which is a very important topic in harmonic analysis, though the theorems there are called restriction theorem. So the principle is you are restricting to a sparse set like the surface of a sphere or so. And it turns out that these inequalities that are proved here, it's about restricting to prime numbers which are a sparse set. And turns out that the method that was used to prove these inequalities just parallel the one from harmonic analysis. Okay. So for as a result, these are called restriction theorem for the prime. So there's no, it must be the Fourier transform. Fourier transform, meaning that's of course very crucial. Yeah, it's this sum here Fn E and T. So it's that sort of a theorem. Okay, so that's why it's called restriction theorem. Anyway, so that being said, let us then get, so these are the properties of V, and using these properties, how does one construct an approximant? So that was where we were yesterday. Right. So now, how does one use this to do the job? So we take, G. Okay. So we follow the same procedure as in the case of Roth's theorem. We convolve f with the normalized characteristic function of a Bohr set. Okay, so here we take S. So we take S to be the set on which the Fourier transform is big. So T in T such that f hat T is bigger than eta of n. Okay. See, the Fourier transform of f, its L infinity norm is less than, that's the L1 norm of, the L infinity norm of the Fourier transform of f is the same is the L1 norm of f, because we are looking at positive functions, and that is less than the L1 norm of v, okay, which is less than or less than n by us here by this property. Therefore, the Fourier transform of f is less than n. Less than n. So, remembering this, it makes sense to consider the set of T in T for which the Fourier transform is bigger than eta n, where eta is a small quantity to be fixed later. Okay, we take S to be this, and BSE as earlier to be the set of n in Z, such that n lies between epsilon n and nt is less than epsilon. Okay. In this case, so just like before, in this case we will set epsilon to be equal to eta. So we will take epsilon to be equal to eta in this particular case. Okay. So I am writing these things just to bring a parallel with the Roth theorem case. Here we take epsilon to be eta, okay, and then we know that BSC, we know, and set B equal BSC, BS epsilon, okay. Here we don't care about having a 3-term AP, we are not interested in that. We only want to produce a dense set, because we have already solved the problem of what happens when you have a dense set. That's Roth's theorem. Okay. So in that case, we convolve with something that is both in the Bohr set and a 3-term AP. I mean, gives rise to a 3-term AP, or the rather the 3-term AP given by an element of the Bohr set, 0b, 2b. Here we don't bother about that part. We just take the Bohr set Bs epsilon, and that is the set we consider, and we convolve. We set G equal F convolution the normalized characteristic function of this. This is a finite set because n is less than epsilon n. Okay. So now we show that this G has various properties that arise from the properties of this function V, because F is itself 1a times V. So via that we will see that G has properties that come from V, from those of V. Okay. So first of all, we know that the cardinality of B, we know that the cardinality of B is bigger than epsilon by 4, some constant by epsilon to the power of 1 plus P plus 1 times n. We know this from the theorem that we proved about Bohr sets, which used this restriction bound. Okay. So without that you wouldn't be able to get that the cardinality of B is bigger than this. Okay. That is known. And then we know that f hat minus G also that f hat minus G hat is of course f hat t. So f hat minus G hat at any t, f hat t minus G hat t is less than this times here you have the elements of the, so you have the Bohr set, and because it's divided, so you just get epsilon here. Okay, so maybe I should just be careful. I write 1 minus the Fourier transform of B by B T like this. Okay. Now here you will write the exponential sum, which is the Fourier transform E and T and in B, and then one will subtract this thing. Use the fact that you have that these n's are inside the Bohr set. So if T is outside S, then f at T is already small. It's less than eta times n. And this you just take a trivial estimate as 2, so you get 2 eta n. If T is inside S, then you use the fact that these are the Bohr sets corresponding to S, and again you get an approximation. So either way you will see that f hat minus T G hat, so you see that f hat minus G hat is less than say eta n. So by this, from which, so you have that this is less than eta n. So that's not a problem. It just works exactly like in the Roth's theorem case. You just apply the fact. So if it's inside S, then when the Fourier transform is big, the Bohr set part gives you the this difference becomes small. When the Fourier transform is small, you anyway have the result. So it's just that. Okay. So you have taken S B to be the Bohr set corresponding to the set on which the Fourier transform is big. So you use that to produce the approximation. Right. So this is the approximation. So eta or epsilon, either way. So you say let us stick to epsilon and write epsilon n. Okay. And now one has to see the. So this is one property that's in the box. Pardon?
For the estimable size of the Bohr set, which function are we using the restriction?
F. Otherwise, you wouldn't be able to get. The same F. Yes, it has to be the same, exactly the same F. Yeah. This F satisfies the restriction theorem, and therefore the Bohr set corresponding to the set on which that F is bigger than an eta times n. That set is large, it is given by this because of the restriction theorem. Because you see the way it proceeds, you discretize, and then you have to count the number of points in the discretization, and that is bounded using the Chebyshev bound, which comes from the restriction theorem for that function. Right? So it's that function that you have to keep track of. So you have this approximation, and then the next thing is, of course, just by the definition we have that sigma Gn is the same as sigma Fn, because sigma Fn, and that is bigger than your delta by 4n. And this results simply from the fact that G is F convolution something, the normalized characteristic function. So sigma Gn is sigma Fn times sigma of this, but this sigma is 1, and therefore you get sigma Gn is sigma Fn. So this is the second property you have for this. And the third property is, thirdly, we have so that was first, second. Now let me see. try to write the third one. Maybe I'll go here. So write the same thing here. Ow. I need these properties too. Okay. So thirdly, we have sigma gn square. So you'll have to do sigma gn square, and that I said yesterday. If you do sigma gn square, and in Z, you use the fact that G is F convolution H, where H is this normalized characteristic function. You expand out the sums, you are able to write this as two functions. So you are able to write this as F convolution. M here, then you have here sigma H convolution sigma Hn Hn plus M, that is one sum, n in Z, here M in Z, times, so this times sigma Fn Fn plus M. Okay, you get this product because G being written as F convolution, this is H. If you wrote out the sum defining the convolution, squared it, and interchanged the sums, I showed you yesterday, I also quoted the van der Koppert inequality as a reference for this sort of a manipulation. But F, of course, is less than V, so this is less than, so this is less than or equal to here. You have M in Z and Hn plus M and M in N in Z. And here you have, this becomes Vn plus M. So here you have N in Z. Okay, and now you split this outer sum in two parts, M equals 0 and M not equal 0. Okay, you have to split this as M equals 0 and M not equal 0, and if you do that, oops, so if you split this as M equals 0, so M equals 0 is going to get you here sigma Hn squared N in Z times sigma Vn squared and the sum n M not equal 0, you have these sums. So for M not equal to 0, we have a uniform bound for this, right? It's less than n. That's one of the properties of V. Property 4. Okay? So you can write, let me make this less than or equal to, and then, or less than, and then I can write this easily as sigma M not equal to 0 of sigma Hn plus M N in Z times N. Okay, here using the property 4, using property 4 of V. And now I extend this summation back to M in the whole of Z, which I can do by the positivity of H. And when I extend it back to M in Z and N in Z, this sum just splits into a product of two sums, namely sigma Hn times sigma Hn. So it just becomes sigma Hn squared. So I finally get that this is less than sigma h n square. So in this times theta n square plus here n times sigma h n the whole square. This is what you get. Okay. Now sigma hn being the normalized characteristic function of a set, sigma hn is 1. Sigma hn squared on the other hand will be 1 by the cardinality of that set. Okay. Because when you square here, you will get 1 by b, cardinality b square, the same 1b, and sigma 1b is cardinality of b. It cancels and it gives you finally a 1 by capital B. So the net result is you see that sigma gn squared n in z is less than theta n squared by the cardinality of b plus n. And this is the key thing that you see Helfgott and Rothon use. This is this property of G. Okay, so now that you have this sigma gn squared is less than this, you want this to be less than, so we would like this whole thing to be less than n, or you want this to be the dominant term. So you you want that theta n squared by cardinality of b is less than n. Okay, or less than or equal to n, you can just say less than or equal to n, which means that you want theta n squared to be less than or equal to cardinality of b times n. But cardinality of b itself has a lower bound, which is this epsilon by 4. So this, if you want this, if you require this, then you can achieve it by choosing your epsilon such that theta n squared is less than epsilon by 4 to the power of constant by epsilon to the power p plus 1 times n squared. If you allow this to happen, then because the cardinality of b is bigger than this times n, you will get that this is satisfied. Okay, and this n square cancels off. So what you have to choose is your epsilon such that theta is less than epsilon by 4 times constant by epsilon power p plus 1. If you chose your epsilon such that this happens, then you're done. For this, again, you see that in order to choose epsilon such that this happens, let me erase this part. So in order to choose epsilon such that this happens, you have to, after taking reciprocals and checking, you see that you have 1 by theta is 4 by epsilon to the power of constant by epsilon to the power p plus 1. So to choose this, you take logs and you see that if you chose epsilon such that 1 by epsilon power p plus 2 is larger than some constant by times logarithm of 1 by theta, then you will be able to achieve this, and from this therefore you will be able to achieve this, and therefore the fact that your this is actually less than n. So you will be able to achieve that last inequality. Okay. So for that, the choice is that epsilon is here to be. Let me see. Have I made? It's less than or greater than. This is less than. Huh? Yeah. The minimum value would be epsilon is greater than 1 by log 1 by theta to the power of 1 by p plus 2. So you choose your epsilon to be 1 by log 1 by theta to the 1 by p plus 2. Okay. So if you knew what your theta was, and what was theta? Theta was the reduction in V in its expected L2 bound, and if you knew that, then your epsilon choice is fixed. It's 1 by log this. Now it turns out that this theta can be taken as something to the order of n, and therefore your epsilon here is going to be of 1 by log n to the power 1 by p plus 2. Okay, and in Roth's theorem, in the second form that we gave, if you remember, there's an exponential c by delta, if you remember from this thing. That actually, if you use an improved form of Roth's theorem, it becomes exponential c by delta to the power of 2 by 3, or 3 by 2 rather, 3 by 2, which, from which, so there's an exponential constant by delta to the power 3 by 2. Here there's a log n. So when you kind of compare these two, you will get a log n to the power of 1 by 3 for the delta. I mean, we'll just see in the remaining few minutes that in fact that explains why you get a log n to the power 1/3 in. So it's a little bit messy thing. There has to be some amount of something. Okay, but these are completely elementary calculations that you just do. They are small comparisons that you make, and eventually you equate the two things and you get. So now with this done, how does one get? So G has all of these properties. It approximates F. Its L2 is bounded like this. Its L1 is bounded below. These tell you that in fact the support is big, because the L2 is bounded by n and the L1 is bounded below. Then whenever you have such a situation, you can always consider, so you have, let me write the other thing here. So you have here the fact that sigma gn square n in z is less than n. So you have these two things, and these two always allow you to get a lower bound for the cardinality of the set on which G is big. So rather than the support of G, one considers the set on which, say, G is bigger than half its average value. Okay, so you consider, say, the set B is the set of n, or S is the set of n, such that G of n is greater than delta by 8. Delta by 8. So then you see how do you estimate the cardinality of S. You have sigma Gn is less than or equal to, or sigma Gn is equal to sigma n in S Gn and n not in S, which is exactly the sort of argument that we used within the proof of Bernoulli's lemma. Now Gn, when n is not in S, Gn is less than or equal to delta by 8, and so this is less than, this part will be less than delta by 8 times the support, cardinality of the support of G. And here n is in S, you use the L2 bound. So you apply Cauchy-Schwarz and you bound this by the cardinality of S to the power of half times extend the sum to the full thing. So you get Gn square n in Z, and this you have bounded by n. So here you will get n to the half. Okay, so this is the way, and now you have a lower bound here which is delta by 4 n. So you use this and the fact that the support of G lies, maximum cardinality is 2 times epsilon n, right? Because G is the F convolved with this normalized characteristic function of B, and B is a set, it's a Bohr set, so all the elements lie within epsilon n. So the cardinality of the support here is maximum n plus 2 times epsilon n. Epsilon is something that is going to 0, it's chosen as 1 by logarithm of n to the power 1 by p plus 2. So for large enough n, this will be very small, and therefore it's essentially n. So you can combine with all this to see that the cardinality of S is bigger than the proportion that comes in here will be delta by 4 the square, because there is a square root on top here, and when you subtract, you see that cardinality of S is bigger than delta by 4, delta by 4 the whole square. So the cardinality of S looks like is going to be something bigger than delta square n. Okay, this is what you will get. The cardinality of S is like delta square n. Actually, you will not take S, but the intersection of S with 1 to n, because you want to still remain in 1 to n, but you know that S lies in, minus epsilon n to n plus epsilon n. So the intersection of S with 1 to n is cardinality of S minus 2 epsilon n, which would still be something like delta square n, because epsilon n is something very small. Okay, so this is the important thing to note, that the cardinality depends on delta square n. And now what are the final steps? Okay, you've got this G, you've got this S. S is dense in 1 to n, it has a positive proportion of the elements in 1 to n, okay, but S is essentially the support of G, which approximates F in the Fourier sense. So what are the comparisons to make? You start with lambda F and lambda G. So lambda F is the number of, so it's this f of x, f of y, f of z, which is the total solutions here, okay, x, y, z in z. But you know that this is such that they are only trivial solutions. So this is less than or equal, and f is bounded by v, so this is less than or equal to vx, vy, vz with x, y, z equal, because they are only trivial solutions to this in the support of f. They are only trivial solutions. So this, and f is less than v. So you get this, which is the same as sigma vx cube. And so from this you can get, by bounding this thing using the Elver norm, you get that this is some n square by, let's say, w of n, where w of n is something in the order of n. So the number of trivial solutions is the number of solutions in f, number of 3-term APs is of order n, essentially. So that's one thing. The other thing is that f and g are close by in the count for the Fourier transform. Pardon? No, it's just some number. I am expressing everything as a ratio with n square as the base. So I estimate this, I'll get something, I just write it as n square by wn. Okay, so it's just something that goes to infinity with n. It has to be, because n square is the order of the total number of 3-term APs. So the trivial ones have to be a small subset of the total number. Otherwise, if most of the APs are trivial, that's not the case, right? So, for any reasonable choice of V, it would be such that it's not concentrated on trivial APs. Otherwise, it's useless. Okay, so that's lambda F. And lambda f minus lambda g, we know that by what we have seen, the configuration control inequality would tell you that this is less than logarithm of 1 by theta to the power of 3 minus p by p plus 2 times n square. See, all comparisons are made using n square, which is the number. Okay, and finally for lambda g. So lambda g is this sigma gx plus gx times gy gz counted over all possible 3-term APs. And since your set S is the set on which G is big, it's bigger than some delta by 2, I mean delta by 8, okay. So this will be greater than delta by 8 the whole cube times the one for the characteristic function of S. Okay, it will be delta by 8 the whole cube times this. But the characteristic function of S, so S is a subset of 1 to n, it's dense, and you're counting the total number of 3-term APs. I have told you that Roth theorem tells you that this is some fraction of n square, depending on the delta. Okay, so that fraction of n square, so this is going to be greater than delta by 8 cube C delta times n square. Okay. So you have a lower bound for lambda g, you know that lambda g is close to lambda f, and you have an upper bound for lambda f. So you run the two against each other, so this n square by wn with this cd delta cube, and when you make plus this thing, and this is really the controlling thing, so this plus this 1 by wn is going to be smaller than log n here. So this is really the controlling thing, and you will see essentially that if you make these comparisons, that your delta should be, if it doesn't have 3-term APs, then your delta would be like delta by 8 the whole cube C delta is less than 1 by log 1 by theta to the power of 3 minus p plus 2 plus some wn. This wn being smaller than this. And your theta is of order log n, that can be checked. So you get here some log n. Now the C delta has to be specified. This from it depends on the version of Roth's theorem that you use. Helfgott and Roth used Bourgain's version of Roth theorem at that point, and that gave them C delta is bigger than let me say delta by exponential constant by so here you have to be careful, it should be delta square, because the cardinality of S is delta square times n. So they had something which went like constant by C delta was delta to the power of 3 by 2 times some logarithm 1 by delta to the power of 3, some smaller order factors. Here if you put delta square, so if you put here delta square, your 3 by 2 becomes delta cube. And you have an exponential constant by delta cube, and here you have something that is log n to the power of this. So when you pass to the logarithms, you get a log n, and this exponential will go away and give you a 1 by delta cube. So if you invert that relation, you get delta is like 1 by log n to the power 1/3. And that's the 1/3 that appears in the denominator in Helfgott and Roth. Okay? Of course, there are smaller order factors which you have to adjust, but the reason why you get the log n to the power 1/3 is because of the version of Roth theorem they use, which has delta to the power 3 by 2 here, which you compare with this, which is like order theta is 1 by theta is like a log n, so you get log n here, and that after passing to logarithms you get log n. This thing doesn't matter, you choose any p between 2 and 3, you get a log n here, which you take the cube root of to get the size of delta, which is why you get that form of the theorem. Okay, it remains of course to verify, write down what is this theta and verify this. These are direct applications of the sieve bound given by Stefan in his lectures. Just directly, you just write down the definition of these things, and you will see that if you apply this sieve bound just like this, you will get these things with this theta of order of log n, and here this is bounded by less than 1. Now, one thing that I didn't have the time to explain is where does the W trick appear? What's the reason for using this W trick? If you try to do this bound, you will eventually, in addition to the n, you will get a log n times z by log z. When you apply the sieve bound to this and simplify matters, you will get something of this sort. So let me just spend 1 minute on this and I stop. So here, when you use the sieve bound to analyze this, you will get n, and then you will get a 1 minus 1 by z to the power of z to the whole power of log n by z log z. This is a part of what you will get. If you just write down what you get by applying the sieve bound to estimate this sum. So you have this extra parameter z. If this z were not there, if z were close to 1, you would get this log n and things would not be bounded. But because you have this extra parameter which you have chosen to be of size log n, and this is bounded by e 1 minus 1 by z to the power z, e or 1 by e as the case may be. So you see that this gets controlled. So this z is needed here to control this log n. So if you choose z to be of the order of log n, then this gets cancelled off, this is bounded, and the whole thing gets bounded by n times some bounded quantity. If you didn't use the W trick, you would get this log n and then you would be sunk. So the W trick here manifests itself like that. Here it's a more subtle manifestation, whereas in the earlier cases it was clear that it was meant to deal with the smaller prime. I mean, earlier case being Green's work itself, it is more transparent. Here it's less transparent unless you work it out, you don't realize, but then it's also quite straightforward. Okay, thank you. That was the end of this course.